Now, one of the most important things I think about learning about lines is being able to take that information and model it with real world data. Okay, so let's take this example that they gave us, talking about a woman's cholesterol and how it's related to her age. Somebody here at the National Center for Health Statistics came up with an equation. Okay, the equation is given as y is equal to 1.1x plus 157. Now, the question says use that equation to predict total cholesterol in a woman who is 50 years old. The first thing I would do is go back in here and really find out what did they give you. We know that y is the total cholesterol, so I'm going to write that down. CHOLES. Total cholesterol. And x is age. It's always helpful if you'll kind of write those two things down first so that we know what y and x are. They're not just strange values. So if I'm asked to predict the total cholesterol, find total cholesterol when a woman is 50. So her age is 50. So I'm given that her age is 50. So I can just take my x value and plug it in to find y. So I say y is equal to 1.1 times 50 plus 157. Do the math on this and you'll find out that y is equal to 201, and the label would be milligrams per deciliter. Okay, so this equation right here and the fact that we know what y and x are is going to be able to help us determine and interpret the slope of the equation. Okay, remember that slope is equal to, hold on, got a phone call. Okay, we were talking about slope. Slope is rise over run. It's a comparison of two things. It's a ratio. It's all of these things. Rise over run, at y's over x's. And in our case, the y's are total cholesterol over age. Okay, we're given in the original equation that the slope is 1.1, and we're going to go ahead and call it milligrams per deciliter, and it's kind of it's over an understood one, you know, because there's not any number down here. So if I wanted to interpret what the slope was, the way I can say this is I can go back to, well, what are my y's and what are my x's? My y's are talking about total cholesterol for a certain amount of age. And this slope says that there's 1.1 milligrams per deciliter of total cholesterol for every 1 year of age. So we can write that in words by saying that cholesterol for women increases, right? It was a positive slope, so it has to increase by 1.1 milligrams per deciliter every year. Every 1 year, so every year. This right here, interpreting the slope, is probably the most important thing I think about, well, one of the most important things about learning lines. Being able to interpret your data for other people. And we do that by really taking a look at, well, what are the y's? What do the y's mean? What do the x's mean? And how are they related? Well, for 1.1 milligrams per deciliter of cholesterol, it's going to increase every year. Okay. Now, what happens if I want to determine and interpret the y-intercept of the equation? Well, let's just kind of scroll back up here. This was the slope, and I better circle that. This was my slope. Okay. Now, the 157, that's the y-intercept already of my line, isn't it? Well, how do I get the intercept. The actual point is when x is 0, isn't it? So if x is 0, then, let me just kind of write this a little bit. If I know that 1.1 times 0 plus 157, because the intercept is actually occurring at 0, 157, right? Kind of going backwards here, but 0 stands for x, 157 stands for y. So that, I mean, that's how we get that the y-intercept is 157. What does that mean in terms of our interpreting our intercept? If x is age, and this age is at 0, then that should be telling us that we are born with 157 milligrams per deciliter of total cholesterol to begin with for a girl, because this is all talking about a woman. So the way I can write that would be that the total cholesterol for a baby girl, or maybe a newborn, is 157 milligrams per deciliters. And that's how you interpret the intercept. So that's kind of important too, because we're saying that at birth you have 157 milligrams per deciliters already of cholesterol. Now, I went ahead and put in here pasted in here basically the graph that was already done, but I did it because I wanted to point out two things. The first thing I want to show you is, see this broken line down here? It goes from 0 all the way up to 140 with nothing in between. The reason that you might see a graph done like that is because there's a lot of blank space. Nothing is happening, in other words, between basically 0 and 157. Remember, when we're born at the age of 0, we start with 157 of this total cholesterol. So this is a way for us to make our graph look a little prettier without having so much white space. The other thing I want you to notice is, remember what our slope was. Didn't we say our slope was 1.1 milligrams? Now how am I going to go, if I started at 0 and I wanted to rise over run, count my slope, if I did that using 1.1, that would be extremely tedious. So instead, what you can do is, we know our intercept, and we know our other point, because we found that to be, for a woman of age 40, it was 201 total cholesterol. So now I have 2 points, and that's all I need to draw a line. I can draw a line with my graph here. So this is a really good example of, although I didn't use the slope and the intercept to graph my line, I did need to be able to interpret my slope. I wanted to be able to tell you what happened on a yearly basis, you know, if you're a woman and you wanted to know your cholesterol. And I also wanted to see the intercept because I wanted to know where does all of this start. So this is an important example to show you that the slope and the intercept is not just for a fast way of graphing, although it really is, but when we get to real world modeling and we see our slope turn into like a decimal representation, we'll probably just pick points to be able to graph it from there.